So we ended last time on percent composition, and this time we're going to talk about empirical and molecular formulas. This is just the reverse of our empirical or our percent composition. So remember, we had the saying where you go from percent to mass, and then mass to moles, and then we are going to divide by the smallest, and then we are going to multiply until whole if needed. So what is the difference between an empirical formula and a molecular formula? Anybody remember? Empirical versus molecular. Yes, Lauren.
Molecular is just how many empirical is the ratio. So sugar is C6H12O6, and the empirical formula there is C3H6.
Okay. So empirical would be our lowest number that we can get to, okay? Whereas molecular are the actual number of molecules, and they are the ones, it is how it exists in nature. So where he said sugar was C6H12O6 as the molecular formula, as the empirical it would be CH2O. Okay. So here, determine the empirical and molecular formulas for a compound that gives the following percentages on analysis. So we have chlorine, and chlorine is 71.65%. Carbon, which is 24.27%. And hydrogen, which is 4.07%. Molar mass is, the molar mass is known to be 98.96. When it says molar mass, they probably mean true molar mass also. So we know that the molecular formula mass, our true molar mass, is 98.96. And it wants us to find empirical and molecular. So we are in percent. So to go to mass, all we have to do is we just turn that to, we take the percent and we change that to grams. Now it says to go to moles. So if I'm in grams, how am I going to get to moles? I'm going to divide each one by its molar mass. So chlorine's molar mass is 35.45 grams per mole. Carbon is 12.01 grams per mole. And hydrogen is 1.008 grams per mole. So we've gone from percent to mass, mass to moles. So put those in the calculator and tell me, what did you get for chlorine?
2.021.
2.02, and that is moles. For carbon, we get 2.02 moles. And for hydrogen, we get 4.04 moles. So now we need to divide each one by the smallest. So everybody's going to get divided by 2.02. And we end up with 1, 1, and 2. So those numbers are our subscripts. And so I'm going to put that in to my formula. If carbon's there, I always put carbon first, and then I put hydrogen, and then whatever's after that. So it would be CH2Cl. And that is our empirical or molecular? Empirical formula. Now it wants us to find the molecular. So to find what our subscripts need to be multiplied by, we are going to take the molecular formula mass, and we're going to divide it by our empirical formula mass. So we are given 98.96. We need to find the mass for CH2Cl. And I got 49.476. And that gives me 2. So my formula for my molecular formula is going to be CH2Cl, put parentheses around them, subscript 2. Or, if you like, you can say C2H4Cl2. Either way.
Would you lose points for writing it ClCH2?
I don't think so. I wouldn't take points off. Any questions on that one? All right, let's do another one. Determine the empirical formula for a compound which is 26.6% potassium. So K is 26.6%, and we know that we can go ahead and change that to grams. Chromium is 35.4%, which is 35.4 grams, and oxygen is 38.1% or grams. So we've gone from percent to grams. Our next step is to divide by their molar mass. So K gets divided by 39.10. Chromium, and that gives me 0.680. Chromium gets divided by 52.00, and that gets me 0.680. And oxygen gets divided by 16.00, and that is 2.38. The next step is everybody gets divided by the smallest. So everybody's getting divided by 0.680. And we should get 1, 1, and 3.5.
Yeah.
Okay, so it is not a whole number, and I can't round up. So the next thing I need to do is I need to multiply everything by a certain number to get it to whole. So 1's a whole number, 1 and 3.5 is not a whole number. So what do I need to multiply everything by to get 3.5 to a whole number? So everybody gets multiplied by 2. So my formula is going to be K2CR2O7. So that's the empirical formula. And now it wants us to get to the molecular formula. And I am going to erase this right here so I can write that. So my molecular formula mass over my empirical formula mass is going to be 294.2 divided by and 294.2, and that gives me 1. So my empirical formula equals my molecular formula, which equals K2CR2O7. Any questions over that? If there are no questions, then we're going to go on to the next problem. Balancing in stoichiometry. Balance the following equation and draw a particular diagram of all reactants and products. So how can we balance this? What kind of equation? This is, we have C2H5OH plus oxygen produces carbon dioxide and water. So how can we balance this? Balance our carbons first. So we put a 2 here in front of carbon dioxide. We have, next I go to my H's. I have 6 H's on the reactant side, and so I need to put a 3 in front of H2O on the product side. And now we have to balance the O's. I have 7 O's on one side, so I need to put a 3 in front of O2. Everybody agree with that? Anybody have any? Okay. Balance the following equation. So we've done that. Draw a particulate diagram. So what they want us to do is following. Let's take, we have 3 different atoms that we're dealing with. So let's just make carbon. It's a black circle. We can take oxygen and make it look like that, and then we can just do a little circle for our hydrogen. So C2H5OH, and OH is a polyatomic. It has to stay together in that. So our chain, our backbone is going to be carbon. So we have 1 carbon, and then we have our second carbon. And carbon can take 4 bonds. One of those bonds on one of these is going to be an oxygen bonded with a hydrogen. So we have our C's, we have our O, And we have one H. Where do the other 5 H's go? We have 1, 2, 3, 4, 5. Next, we need to draw 3 O2 complexes. So there's one. There's another one. There's another one. And if you kind of get in your mind how these look, just draw. If you can start looking at it that way and drawing it that way, it makes it easier. Now we need our carbon dioxide complex. So we know that carbon is in the middle. We need 2 of those in the middle. And carbon dioxide is linear, so then we have oxygen on either side. And then we need 3 waters, and water looks like little Mickey Mouse here. Have all of our oxygens and then our hydrogens. So you must be able to draw those. I don't care if you use some other way, you use colors or however you're using them, but you must be able to draw them for quizzes and exams and labs. Any questions? Everybody good? Oh. Are we ready to go to the next step? All right, so we're actually beginning the stoichiometry here. I know you've been taught by different teachers, and I'm going to show you how I like it to do this. I just kind of read the question. As I'm reading the question, I'm going to be writing things above the equation that helps me out. Determine the amount of iodine. So I go to my equation and I see I2, and that is what I'm looking for, the amount. So I put a question mark there. When 145 grams of Ki, so above Ki, I'm going to put that I have 145 grams. React with excess copper to chloride. So I am stoiching from Ki to I2. So we first start with what we are given. We are given 145 grams of Ki. And for me to get anywhere from Ki to I2, I need to get to moles. So how am I going to get my grams to moles? Molar mass of Ki. Put that in and see what you get. I got 166 grams of Ki. And that is in 1 mole. Grams goes away. We're in moles of Ki. I need to get to I2. So now I can stoich it to the mole bridge. So for every 4 moles of Ki, I can produce 1 mole of I2. And now I need to get my moles of I2 to grams of I2. So we need the molar mass of I2. The molar mass of I2 is, anybody get that? I have 253.8 grams of I2. Put that in there. Tell me, how many grams of I2 can we make? What'd y'all get to 3 sig figs? 55.4, yes, thank you. 55.4 grams of I2. We're going to do the last one here. We're going to do 31. I don't even know if I have room here to do 31. But we'll try it. Baking soda is often used as an antacid. It neutralizes excess hydrochloric acid secreted by the stomach. Milk of magnesia, which is aqueous suspension of magnesium hydroxide, is also used as an antacid. Which is the more effective antacid per gram, baking soda or magnesium hydroxide? So what I need to do is I need to stoich baking soda to hydrochloric acid and magnesium hydroxide to hydrochloric acid. So I'm going to have 2 running problems here. I'm going to have baking soda and I'm going to have milk of magnesia. The question says more effective per gram. So each one starts out with 1 gram. We start out with 1 gram of NaHCO3 and 1 gram of magnesium hydroxide. I want to take this gram and I want to turn it into moles of hydroxide or hydrochloric acid. So we need the molar mass of NaHCO3. I got 84.01. So I am in grams of baking soda, and I need to get to moles of hydrochloric acid. So what's the ratio of baking soda to hydrochloric acid? It's a 1-to-1. All right, solve that and tell me what you get. How many moles of HCl can we neutralize? To 3, let's just go to 1 sig fig, since we just have 1 gram. 0.01 moles of HCl. Now we need to do the same thing for milk of magnesia. I have the molar mass of milk of magnesia as 58.33 grams. And the ratio this time is a 2/1. So for every 2 moles of hydrochloric acid, it's 1 mole of MgOH. So to 1 sig fig, what do y'all get? 0.03 moles of HCl. So what should you take if you have heartburn? What's going to be the most effective? Mom.
But what, isn't it an aqueous solution?
Mm-hmm.
Isn't it diluted then?
That is it in that solution as an aqueous. So mom is going to be the most effective. Are there any questions? So tomorrow there's one more that I want to do, and I'll do that tomorrow, and then we're going to get into limiting reactants and combustion. And then you have your homework, which is which one is E, F? I'm so confused.
G.